Welcome to this explainer. Today, we're jumping straight into a seriously fascinating piece of technology developed for the Indian Air Force. We're going to unpack the exact hardware and software that allows a military grid to track what are essentially invisible drone threats. We're talking about the Ku-band Active Electronically Scanned Array, or AESA, radar system. And this isn't just about spotting a random dot on a screen. This is an incredible story of physics, hybrid artificial intelligence, and split-second edge computing, where missing a target by even a fraction of a second is just absolutely not an option. So let's start by framing the sheer scale of the physical challenge here. When most of us think of military radar, we usually picture those massive spinning dishes tracking fighter jets or ballistic missiles way up in the stratosphere, right? But the modern battle space has completely shifted. The real challenge today is detecting something incredibly small, flying really close to the ground, miles away in a sky literally full of clutter, things like trees, buildings, and weather. Traditional standard radars, they're virtually blind to these micro threats. To really wrap your head around the scale of this problem, let's look at the numbers. The specific drones being targeted by the Indian Air Force have a radar cross-section, or RCS, of just 0.01 square meters. To put that into perspective, trying to bounce a radar wave off a surface that small is mathematically like trying to find a tiny bird from 3 to 5 kilometers away. And when you factor in the physics of signal degradation over that kind of distance, which is known as the path loss penalty, the returning radar echo isn't a loud ping. Actually, it's practically a whisper. As you can see in this comparison, classical X-band radars, which make up the bulk of existing military infrastructure today, just flat out struggle to catch these tiny targets. Their wavelengths are just a bit too long, and they fundamentally lack the sensitivity to hear that whisper. And that is exactly why the solution is this purpose-built Ku-band AESA system. See, Ku-band operates at much higher frequencies, with a tightly packed wavelength of roughly 2 centimeters. That shorter wavelength is absolutely optimized for bouncing right off the tiny carbon fiber bodies of commercial and tactical drones. Now, the physical hardware that makes projecting those dense Ku-band waves possible is a massive leap forward. The secret sauce here relies entirely on gallium nitride, or GaN, power amplifiers. While older legacy systems used gallium arsenide, GaN gives you 3 times the power density. It's what gives this radar the sheer brute force needed to push those high-frequency waves straight through the atmosphere, ensuring that the tiny echo bouncing back from a 0.01 square meter drone is actually strong enough to trigger a real detection. I love how this breaks down the hardware, because it's essentially a beautifully engineered brute force engine. It operates deep in the 13.5 to 15 gigahertz range, and it completely ditches the giant, slow spinning radar dish. Instead, we're looking at a planar array packed with 256 to 512 individual patch elements, with each one continuously pumping out 5 to 10 watts of power. But here is the real game changer. Because it uses electronic beam steering to dynamically shift the waves, there is absolutely zero mechanical rotation lag. It can look far left and then instantly look far right, basically at the speed of light. But, raw physical power isn't quite enough to secure a complex battle space. What really blows my mind is the detection-to-action pipeline. It's this hyper-fast, deterministic kill chain. The whole architecture is built around a punishingly strict latency budget. From the exact microsecond a wave bounces off an incoming drone to the moment the operator's screen flashes red, the system is engineered to take absolutely no more than 200 milliseconds. Let's break down how that 200 milliseconds is sliced up, because it is a total masterclass in edge computing. First, RF echo acquisition takes less than 20 milliseconds. Then, the field programmable gate array crunches the complex digital signal processing in under 50 milliseconds. After that, the AI steps in to classify the threat in under 80 milliseconds. And finally, it fuses all that data and queues the command grid in under 50 milliseconds. Think about that. In the literal blink of an eye, the radar has found the threat, processed it, and alerted the grid. No buffering, no lag, just real-time action where a fraction of a second literally means the difference between life and death. So that brings us to a massive and honestly kind of funny hurdle in radar physics. Let's say your ultra-sensitive radar perfectly detects a 0.01 square meter object hovering exactly 5 kilometers away. How do you actually know what it is? The radar just sees a tiny dot. Is that an enemy quadcopter carrying a payload? Or is it literally just a pigeon riding a thermal draft? If you sound the alarm for every passing bird, the system instantly becomes totally useless because of false alarm fatigue. And this is where the technology stops acting like a simple sensor and basically becomes a superpower. Standard radar only sees the main body of the object moving, but this Ku-band system is so sensitive, it can read what are called micro-Doppler signatures. That means it isn't just seeing the drone moving forward, it literally detects the specific rapid frequency modulations caused by the spinning rotor blades. A bird's flapping wings create a completely different acoustic and radar signature on a spectrogram compared to the rigid high RPM buzz of a quadcopter. To actually make sense of those micro-Doppler signatures, the system uses a highly active, three-part hybrid artificial intelligence brain. The convolutional neural network aggressively analyzes the spectrogram images. At the exact same time, a transformer model tracks the temporal motion patterns, while an LSTM model anticipates exactly where the object is going next. All of this is running constantly on ruggedized NVIDIA Jetson Orin edge computing hardware. And the result? An incredible 95% accuracy rate in telling birds apart from drones, doing it consistently in less than 100 milliseconds. All right, let's zoom out to the macro level for a second. Because a modern drone attack is rarely just one isolated drone, right? We are firmly in the era of automated swarms. To handle this, the system uses a complex algorithm called Joint Probabilistic Data Association. Simply put, it untangles intersecting flight paths like a knot of string, which allows the radar to track 50 or more fast-moving drones simultaneously on a single screen. It flawlessly maintains that track even if the drones maneuver wildly or duck behind a building. Now, this radar definitely doesn't operate in a vacuum. It acts as a seamless plug-and-play node in the larger counter-unmanned aircraft systems grid. The second the AI confirms a hostile track, it publishes that targeting data using standardized APIs and incredibly precise time synchronization. We're talking under 50 nanoseconds of jitter here. That hyper-precision allows the overarching system to instantly aim electro-optical cameras right at the target and immediately cue RF jammers to disable it before it gets any closer. But let's ground this all in reality for a minute. The smartest AI and the best hardware in the world are completely useless if they can't survive in the actual field. So this entire system is designed for rapid tactical mobility. The ASIN panel is securely mounted on a 4x4 light tactical vehicle using a heavy-duty telescopic mast. It's built from the ground up to handle harsh deserts, corrosive coasts, or cluttered urban canyons. Plus, it's totally shielded against dust, water, and intentional electromagnetic interference. And, in modern warfare, if you stay in one place for too long, you become a target. That's why this relies heavily on a shoot and scoot philosophy. Check out this timeline. A standard two-person crew can go from driving a parked vehicle to managing a fully operational radar grid in exactly 15 minutes. They position the vehicle, drop the outriggers, raise the mast, power on, calibrate, and start scanning, often way before the enemy even realizes a detection grid has been set up in their sector. Oh, and they can do all of this entirely under the radar, quite literally. Traditional military radars use these incredibly loud, clunky diesel generators that produce massive acoustic and thermal signatures. They practically announce their coordinates. But this system uses a high-capacity lithium iron phosphate battery backup. This allows for 4 to 36 hours of completely silent operation. And operating quietly isn't just nice to have, it's a massive tactical survival advantage when you're trying to stay hidden. So, as we wrap up this explainer, I really want to leave you with a provocative thought. We've just seen how this Ku-band ASAS system uses advanced GaN hardware and micro-Doppler AI to spot the invisible and react in a staggering 200 milliseconds. But the technology of war, it never stands still. As defensive tech speeds up to these split-second reaction times, what happens when the offensive drone swarms get even faster, more autonomous, and more erratic? It's a completely high-stakes arms race of computation and physics, and understanding these systems is the first crucial step in seeing exactly where the future of defense is headed. Thanks so much for learning with me today.